So I'm just making a review here anyway. Here, if you use two force members, you don't have to use any equations. Here you can use one moment equation. And here actually you use all of the three equations have to be used. If you have a three force member or four force member or whatever, you have to use all the equations you have in your hand. But usually these three would be, in most cases, enough. Well, not always, but you have these equations, you have these members. Of course, you might have a four force member or four force member and a moment member, etc. In which case you have to use the static analysis equations. Okay, then the last week I tried to solve some examples like a four-bar mechanism, an inverted slider crank mechanism, etc., in which we tried to identify the forces and the unknown force, tried to solve for the unknown force in the static force analysis. That's what we did the last time. You can maybe one thing we can talk about is the superposition. Superposition is something we commonly apply in engineering, but superposition assumes that the equations must be linear, okay, in the variables. If they are not, you cannot really use superposition. And fortunately for us, the static equilibrium equations are linear. So we can use superposition, at least for the non-frictional case. For example, what do I mean? Let's say that you have a four-bar mechanism like this one by superposition. Well, analyzing a four-bar mechanism, let's say that you have F13 here, and let's say F14 there. Two different forces acting on the mechanism. And let's say that there is a T12 which is unknown. Well, the last week, as you might remember, we tried to analyze mechanisms with one force only, okay, like F14, in which case things were easy, kind of easy, because this one becomes a three force member, this is a two force member, this is a two force and a moment member, and you can quickly obtain the solution. Actually, we sort of got the solution analytically. What we can do is, in superposition, do the following. You can consider, let's say, F13 only, and assume that F14 is 0 here, okay? And get one solution for T12. So this will be T12 prime, let's say. And then as a second step, then you consider F14 only. This will be T12, let's say double prime, okay? In this case, we assume that F13 is 0, okay? So we get two solutions for two different forcings. So the total solution in which the both forces applied T12, in which F12 and F13 is applied simultaneously, will be T12 prime plus T12 double prime. Okay. So this is the method of superposition. It might simplify the matters. You can, of course, solve the problems without the superposition as well, but it might probably be more lengthy, longer than the one we are applying here. And the second thing is very important, that superposition applies if the equations are linear in the variables. Okay? You cannot apply superposition if there is any nonlinearity. Don't forget that. Okay. Any questions up to here? Now we will continue with systems with resisting forces. That are basically, we assume some kind of dissipation or friction. Now, here we have to differentiate between types of friction. And usually this is something confused. The static friction, let's say. Static friction is the friction in which there is no motion. Okay, so let's say that we have an object like this one. Okay, it is on the ground. Let's say this is member I, and let's say that the ground is J. Well, the object is standing still, okay? It is not moving, so that the velocity of the object, Vi, is exactly 0. It is static, that is. Well, the forces acting on it is going to be, well, there will be a, well, doesn't matter really, but there will be an mg force. There might be an external force, like F, let's say, doesn't matter. Now there will be the reaction force, let's say, Fji, okay, which is, in static case, it will be equal to mg, but this is the force applied by the ground to the ith member, let's say J is the ground. And then there will be a static friction force if the member is not moving. Actually, it has to be something that prevents the motion, right? So let's call this Rji. Rji is this friction force. Well, static equilibrium tells us that Rji must be equal to F, right? Minus F, as a matter of fact. But there is, let's say, the friction here, mu static coefficient of friction, but also the Rji force must be, well, not equal, but rather less than or equal mu s times Fji magnitude. Okay. Which means that there is a limit to the static friction force, okay? If you increase this external force F up to the limit in which Rji becomes well, less than, well, greater than US times FGI, in that case, you cannot sustain the static position. The object has to start moving, in which case we will have dynamic friction. So here we have no motion, as you know. But the important thing here you should take is this, that in the static friction force, the static friction force, Rji, is not equal to mu s times the normal force, like Fji. Okay. It is less than mu s times Fji. It is equal to the external force acting on the object if there is static friction, if there is no motion. Okay. This is important. Well, if the motion starts, if there is some motion, there is dynamic dry friction. In the dynamic friction, now there is some external motion. Sorry, there is a motion and an external force there might be. Just a second. Anyway, let's say that we have friction here. This is again I. There might be an external force F here. Now the object is moving with a velocity v, which is not zero anymore. There is F Ji, there is mg. There is the resisting static, well, dynamic friction force now, Rji. Now, in this case, Rji is independent of F. Rji, the static, the friction force is independent of F, and it is equal to kinetic friction coefficient or the dynamic friction coefficient times Fji when there is motion. The Rji now, the resisting force is a function of, well, it is a constant force independent of the external forcing. Okay. So these are the dry friction, and then the third one is the we use to model is the viscous friction model. We know this also. If you have a like an object moving with a VI, okay, the resisting force Rji rather, Rji is going to be minus c times, we can actually even use vectors. This is some constant times c times I. It is in the opposite direction to the velocity. Now, as I have said before, this is a simpler model. Because it's linear. Okay. Actually, the actual equation, I didn't write it down here, but Rji if you write it properly, the RJI should be as a vector, it should be something like, by the way, here I shouldn't have a vector here, right? This vector. It is. It is something like this. This signum function, as you might remember, is signum is like x equals 1 if x is greater than 0, and minus 1 if x is less than 0. So it is a strange function, and that has to be a minus, by the way. Yeah, that has to be a minus. So signum function is, since it is nonlinear, the dynamic friction changes its direction when the velocity changes. Okay. Which makes it very difficult to model, actually. So therefore, using the viscous friction in our models in some cases might be simpler. Okay. So these are the three modes of friction. If you use, let's say, the joints, the common joints we have are the prismatic joint is one of them, and that's what we have been using in the examples above. Let's say that we have again an object in a prismatic joint. Let's say that we have an external force acting on it. Let's do it. Some external force like F1I. So this is member I again. There might be a force acting due to another member like FKI. Okay. This is J. There might be a ground force FJI. And then you have a velocity. And let me use another color for the velocity. Let's say EI, like this. And then there is the resisting friction force. Let me use this one. Again, R, JR. RJI is the frictional force. Now, the forces that act because of the Jth member, which might be the ground or some other member, it doesn't really matter, are the following. There is FJI is a force that acts upwards, FJI. And then there is RJI, which is due to the member I, actually the resultant force that acts is a vectorial combination of these. I'm using the notation of the book, so Fji resultant. Okay. The resulting force would be this one. Now this angle, phi, is called the friction angle. It's the angle between, let's say, Fji and the resultant force. And as you see, for this angle, tangent phi is equal to Rji over Fji. Okay. And assuming that there is dynamic friction, there is motion here. It is mu k times Fji divided by Fji, right? Which is equal to mu k. So the tangent of phi the friction angle, the tangent of the friction angle is equal to the kinetic coefficient of friction, as you see, if there is motion. And the force that you apply on the member, you can show it like this. The forces acting on it would be F1i, Fki, the external forces, and then there will be Fji resultant, which acts with an angle of phi with the vertical, as you see, phi being the friction angle. So the ground force and the friction force can be combined as a single force, which makes an angle of phi with the vertical, and phi angle is called the frictional angle. Now this is for the prismatic joint, okay? So it is possible to use friction angle for the prismatic joints, and for the second important joint we have is the revolute joint, or R joint, let's say, in which you have something rotating inside a circle, let's say, concentric circles rotating with respect to each other. Revolute joint is like a pin joint, as you know. It is like you have one member here. There is a pin. That connects it to another member, right? Something like
Hocam,
this.
apologize for interrupting. Can I ask you a question about
Yes,
the previous
sure.
one? So the angle phi is constant even though the acting force, the angle of the acting force is changing, right?
No, well, angle phi, yes, of course, yes,
And
yes.
F,
Yes, phi is a property that depends on the friction coefficient only, right?
oh,
It doesn't depend on the amount of forces. Do you
okay, hocam.
understand?
Yes.
Well, the RJI and FJI can change, but their ratio remains constant. Okay. So,
Okay hocam.
okay. So in the revolute joint, there is a pin that connects both joints. Well, forgive my drawing. It's very poor, but I think it sort of makes you understand. There is a pin that allows relative rotation of two objects. I'll do a exaggerated drawing of this now. Let's say that I put it under a very large microscope or something, so that we see it's a huge, this pin joint is seen from this side. You know, we look at it from this side and we see, let's say, the following. I don't know, how do I draw this? There must be a way, there was a way. But, yeah. I want to draw a circle, if I may. Okay, that's not too bad. Select this. Okay, kind of. This is, let's say, the pin. It's in contact. What happens here? We have there's a contact force. Sorry, like this one. Let's say this is the pin. Let's say this is I, and let's say this is J outside. Okay. There is a contact force of FJI. Omega Ji is the relative angular velocity. Now, there is a resisting force, frictional force, like, it shouldn't be this big, right? Something like this. RGL, okay. Now, combining these, we have the force acting would be FJI, and the resulting force is this one, okay? And this force now, FJI acts towards the center of this, as you see. Whereas this FJIR would be acting like at a smaller circle. Yes. Let me go there. Okay. this FJIR is going to be tangent to this circle, which I have drawn here. Now, this circle, I will say that this original circle has a radius of r, and this small circle in which this FJI resultant is tangent to has a radius of RF, let's say. Okay. Now, this angle, as you know, is phi. Therefore, this angle is phi. And this is r. So we see that tangent phi, which is again is equal to Rji over Fji in our case, which is equal to mu. Let's say mu, not mu k. Here in this picture, in this geometry, as we see here, if this is R, this is RF, and if this is phi, R sine phi, and this is approximately equal to R tangent phi if phi is small. Which means that RF is equal to mu or R times mu. So here R is the radius of the joint. RF is the I didn't define it, but let me define it now, of the friction circle. RF is called therefore the friction radius. Okay, so for revolute joints, we have a similar way of treating the friction problem. We define a circle with a friction radius. One thing is omega, the direction of this angle is determined from omega because Rji opposes omega ji in direction. Okay. So you have to know or guess, be able to guess the direction of the omega ji. Omega ji, which is the angular velocity, at least you should know the direction of omega ji. Let's say in direction, at least. Well, not must, but can be found from velocity analysis. Another thing is, if you want to do well, you can use this friction circle. But actually, if you are doing analytical work, that is trying to find the resisting forces, it's not the resisting force that is important here, but rather the resisting moment because of the friction is more important. And let me try to show this to you. Okay, in the point of contact, there is Fji, the contact force, and there is the friction force, Rji equals mu Fji. Okay, so it's a combination of these. This is omega Ji. Actually, this you can isolate and write as follows. This will be, okay, the Fji will be there. But the force, the Rji force, its main effect, actually, it's not going to be a force acting on there, but more like you can replace it by a moment, okay? The friction moment. If this is has a radius of, let's say, r here, okay? And you might have a mji, and mji is going to have what? Mu times fji times the radius. Well, of course, the rji can also be carried here. Rji, which is mu times fji, but this is usually negligible. Okay, you don't have to carry this rji. Instead, it's only the frictional effect, the moment effect of the friction is important. Okay, so in a sense, in a revolute joint, the frictional force creates a resisting moment. Okay, yeah, this kind of resisting force you can kind of ignore in most of the cases. Okay, well, the time passed quickly, so let's take a break here. I will continue. Let me share now. Now, as we see from here, the moment of the friction force depends on R. And if R is small, then Mij is going to be small. Okay, which means that the moment effect is not going to be very important in the revolute joint. For small revolute joints, you can ignore the friction. Okay, it's not such an important effect. But for prismatic joints, you cannot do that. But for revolute joints, it's not that important, really. But there is a problem in Eres Hoca's book, which has a huge revolute joint, as you see, which I have copied here. This is from page 366 of fifth edition of the book Mechanisms. Okay. Here we want to determine the well, we assume that there is friction in all joints. So we assume that the friction coefficient is 0.1 in all joints. In both prismatic joints, in the prismatic joints and also in the revolute joint. So this radius is a very large one here, R23, let's say. The other radiuses are small. So R12, which is the radius between 1 and 2 here in this joint, and the radius between 3 and 4, R34 is like 50 millimeters, which is not too small, but small. R34, on the other hand, sorry, 23, on the other hand, is 250 millimeters. So this distance is 250 millimeters. F14 is given as 100 newtons, this external force. And then we want to determine the torque, this T12, okay? We assume that there is friction in all of the joints. I want to solve this example, let's say example here, as a conclusion to static force analysis. Okay, now this will be an example which shows us how you approach a static static problem with friction. Well, as usual, we start with drawing our free body diagrams for each link. Well, links are, the second link is a little bit strange here. It is an eccentric circle, as you see. It is a circle that is placed in another circle. So it acts as if it is a, what can I say? As if it is a revolute joint. The distances are given. A0A is 200 millimeters, AB is 800 millimeters, etc. And A0B is given as this distance. The angles are given also. Theta 1, 2 is 55 degrees. Anyway, let's draw the free body diagrams. Now, for this link 2, well, we can draw it like this. This is A0. I'm drawing A0A here. A0 is here, A is there. Okay. Well, there is T12, the external torque, which we want to find. Then the forces are, well, we don't know the forces, but we know that they are equal in magnitude, opposite in direction. There is G12, there is, and this, they shouldn't be actually, like, they shouldn't look like they are G12, and they are right angled. So this is F32. On top of that, there are frictions now, friction things. So here you have mu R12, G12. Okay, this is the frictional moment. And here you have mu R2, 3, F3. Still, as you see in this link 2, the unknowns are T12, G12, which is equal to F32. We know that they are equal. The friction doesn't introduce an extra, let's say, doesn't introduce an extra unknown to our problem. The only thing is we should be determining the friction direction. Okay. If you are given that omega 1, 2, let's say, is in this direction, is in the clockwise, then if this is omega 1, 2, then as you see, the couples should be opposing that, and they do. Okay, the frictional couples should be opposing that. Okay, this is link 2. Link 2. For link 3, this is A, this is B, this is B. Well, it was in the non-frictional days, it was a two-force member, not anymore. F23 is here. The forces are equal in magnitude, opposite in direction, of course. This is F43. They are equal in magnitude, opposite in direction, but there is also frictional forces now, which is equal to well, this has to be opposite. Mu R23 F23. And it has to oppose that. And this one, mu R34 F43. Okay. These forces, well, they should be parallel. F43 and F34 should be equal. Well, yes. Okay, and finally we have the fourth link, which is the this distance is A. A is 50 millimeters. Well, the distance it has. And let's say that this force acts at B, and the distance between B and T14 is S. Well, that's one thing, but there is also the frictional moment, which is mu R34 F34. Okay, we are going, this is link 4. We are going to write three equations, as you might remember, for each of our members. And remember the following. if you sum up the forces, G12 is equal to F32 is equal to F23 is equal to F43 is equal to F34. As we know. Okay, that is all these forces starting from G1 to F3 to F323, F43, and F34 are equal. Their directions are different, but they are equal. On the other hand, let's remember the following. This is important, as I said before. Let's say if you have a link with alpha that has a length of A, and if you have a force Ff with an angle beta, okay? And if you take a moment about point O, the moments about O is equal to AF sine beta minus alpha. I showed this the last time. This is an important equation because we encounter it all the time. And by the way, let me show the angles on the free body diagrams. This is beta 1, 2. Beta 1, 2. Yes. And let's say that this angle is phi. Phi angle is not the friction angle, okay? It is the angle of this F43 and the horizontal, okay? It has nothing to do with friction angle. Okay. So from here, we start writing our equations for link 4, let's say, start. The forces, sum up the forces here, x direction, minus tan. This angle is phi, for what angle will be phi? This angle is going to be phi. The horizontal component minus mu G14 minus F14 equals 0. They are all in the negative x direction. By the way, we ignore the linked what is weights. So we don't put an mg on the links. We can, it will just make the problem a little bit more complex. But we don't, well, we ignore the link lengths. Sorry, the link weights. G14 minus F34 sine phi equals 0. And we have to take a moment somewhere. Let's take a moment about D, which is this point. There is already a moment, which is mu R34, F34. So let's write this. R34, F34 is the moment. Minus S times Z14 minus mu times Z14. Okay, these are moment creating forces. So here, if you look at it, Unknowns are phi, G14, F34, and T12 is an unknown. T12, and there is an S. So these are the we will see that they are the unknowns. This is link 4, then we will go to link 3, let's say. Link 3. Let me show it here. This is link 3. We will take a moment about some point. Let's take a moment about point A, in which case we use the fact that the forces are equal in magnitude, opposite in direction. So we will just take a moment. A2, oh, sorry, A3. Okay. This is the equation we will use for link 3 only. And for link 2, again, we will just take a moment. Where was it? It's similar. We will take a moment about A0. Yes. Plus, there is the external torque which we want to find. It is equal to 0. Okay. Let me go back. As you can see, this angle is phi as well. This angle is something we don't know, but we will find. So this is phi. Okay. Well, we have actually, as you see, 5 unknowns, and here you have 5 equations. Well, it looks like there are unknown, there are also these equations that all these G12s, all the forces are almost equal to each other, except a few of them. So we have 5 equations with 5 unknowns, which is kind of solvable. Well, I'm not going to go through all the steps of solving them. Let me give you the solution. Actually, it is given in the book. Phi angle is 166 degrees. F34 is 105.6 meters. T14 is 25 meters. Millimeters. And T12, which was the original question that was asked, was 22.9 Newton meter. Okay, this is the solution. On the other hand, if we had assumed that mu is 0, that is, if there is no friction on this problem, the T12 would be minus 20.43 Newton meter. And the difference, as you see, there is a difference, but even with this huge revolute joint, eccentric revolute joint, the difference is not too much, okay? Even here, if we had ignored the friction in the revolute joint, we wouldn't be too much mistaken, actually. Well, we would be mistaken to a certain extent, but not too much. Okay, do you have any questions? Actually, this will conclude the static force analysis. Obviously, you will have to solve many questions in order to familiarize yourself. And remember that the static force analysis is just an approximation, as it's a first step in analyzing the mechanism, force analysis of the mechanisms. What we really want to do is the dynamic analysis, which I'm going to start now if you don't have any questions. So I will make a very brief introduction for today. And probably we will have to reserve the most of the work to the next lecture. So let me start. We will start dynamic force analysis, which is the subject of, you learned in the subject of dynamics, as you know. Let's start with some definitions. The particle is object, let's say, with small dimensions, so that the particle, well, does not appreciable magnitude in order to have rotations about itself, whereas the rigid body, what we call the rigid body, which we use, object, let's say, with appreciable dimensions. The important thing is the distances between 2 points inside, let's say, is constant. That's what we mean by rigid body. So a particle is like a dimensionless body, okay? Whereas a rigid body is like this one, okay? Like an egg, and A and B are two different points, particles. And in between, the distance AB is constant, so that it is rigid, so that it doesn't extend, it's not elastic. Or more mathematically, RB relative to A as a vector is constant. Magnitude of the RB relative to A vector is constant, okay? Well, the basic property of rigid bodies is rotation, okay? The rigid bodies can rotate about their own axis. So a rigid body like this one has an angular velocity omega, and it has an angular acceleration of alpha. So the omega is the rate of change of all angles inside the rigid body. and alpha is the rate of change of angular velocities. This is a property of the rigid body. It's not, you cannot have two different omegas inside one rigid body. There is only one. Okay. Now, a rigid body has, we said that it has appreciable dimensions. So again, let me draw one. Something like this. Let me draw the coordinate axis. We can define in a two-dimensional rigid body, it's made up of small masses like Mi, Mj, whatever, well, small masses like M1, M2, etc. You can add up all these small masses, and each of these masses have a position vector, as you see. Let's say this is Rj. This is Mi1, R2, etc. We can sum up these Ri times Mi's, whatever. Well, there are infinitely many of them, but then divide it to those small masses to obtain a point which will be the mass center of this body. And let's say this is G, and this will be Rg. The mass center is defined as the weighted distance of the small masses inside the rigid body. Actually, this can be eventually in the end, this becomes an integral, and this is R. So it is the mass center of a body is defined with respect to a coordinate system, but it is a point inside the body, but it can be outside the body as well. But the mass center, as we will see, will represent the mass in the dynamic equations. So the mass center is an important property. And this is the first moment, is obtained from the first moment of the masses. The second moment of the masses gives you also a very important property. It gives you the mass moment of inertia. Okay. Let's say that you have a nice one. Okay, something like this. Let's say that you have xy coordinates. This is y, this is x. Okay. Well, any point here, this is x, this is y, this is r. Okay, well, r is this distance rather. Let's say that we attach a coordinate system to G, mass center of the object, okay? We define it to be Ig as the second moment of the mass, which is R squared En. And it has a unit of kilogram meter squared, which we can write as integral, if you like, x squared plus y squared. Okay. Well, this is actually well, in 2 dimensions, it's kind of easy, but with respect to an axis. So here, actually, the axis about which this IG is the axis which comes out of the screen, the page, which is the z-axis here. But I don't want to go into details because it's more important in 3-dimensional dynamics. But keep in mind that it is defined with respect to an axis. There is one more property, which is called the radius of gyration, in which we assume that I about a point, let's say that IO is mk squared, where k is the radius of gyration k. If you define an inertia of an object as mk squared, and the radius of gyration can be found from I0 over R. It is the inertia divided by mass, and you take the square root. Basically, it tells you if the mass of your object were to be concentrated at the rim of a ring, how much would the radius of that ring be? Okay, that is what this thing shows. So if you have a, let's say, ring of mass m, okay. I should say mk is 0. This is 0. As you know, the ring has a mass of IO, if this is O, would be m ko squared, okay? So if you have an irregular object, okay, and if this is point O, it doesn't have to be the G point, it's just any point inside the body. If you take all the mass and concentrate all the mass of that object in a ring, hollow ring, so that the inside is empty, how much would the radius of that ring be? So radius of gyration, KO is, let's say, measure of inertia, mass moment of inertia, or I should say, okay, inertia, I should say measure of rotational inertia. Inertia of a so the more K0 is, it has more rotational inertia. And also, one last thing is parallel axis theorem. You know all these things from dynamics, so I'm going rather quickly. So let's say we have an object like this one. Why don't we get a nice egg? Okay. Well, let's say that this is the centroid or mass center. And let's say that we have Well, another coordinate system like x prime, y prime. Okay. Let's say that this is O. Okay. And if this distance is r, basically it says that parallax theorem, if you derive it, it's not too difficult to derive, but it says that I O with respect to O is equal to IG times plus, sorry, mr squared. Okay. So for about we can carry the mass moment of inertia to any other point other than the mass center. The minimum mass moment of inertia occurs at the mass center. Remember that this is an important theorem which we constantly use. Okay. Then we finally come to Newton's second law, which is the fundamental law in, well, we use in mechanical engineering. Basically, for particles, we just use the summation of all forces is equal to mass of the particle times its acceleration. Okay. For rigid bodies, this is, you can derive, we have derived this in dynamics. The summation of all forces on the rigid body is equal to mass times acceleration of the mass center. Okay, G is the, as you know, the mass center. Well, on rigid bodies, there is one more thing which is extremely important, the moments. The summation of moments is equal to Rg, mass moment of inertia with respect to the mass center, times the angular acceleration. Actually, this is also this is true for plane, well, okay, it's true in general, but in 3 dimensions it becomes more involved. So basically, we have, let's say if you have a rigid body acted by different forces, F1, F2, F3, whatever, F4, doesn't matter really. This should be equal to, as we know from statics, this eventually reduces to forces and summation of moments about a point, which we select to be the mass center. And this is also equal to summation of all forces is equal to MAG vector. This for these forces are equal to this. And summation of all moments is equal to IG times alpha. Maybe I should use a different color about this. Okay, so the moments are in red. Just to, identify. So in plane, if you have a plane rigid body, this reduces to summation of forces in the x direction is MAX. Summation of the forces in the y direction is MAY. It depends on your coordinate system. You can use r and theta or tangential normal directions as well. And the summation of moments about the mass center is equal to Ig times alpha. So for a rigid body, you have three equations in general. Well, you can use, if you have a rigid body fixed at a certain point, let's say O, you can use the following equation, sigma MO. Summation of moments of all forces is equal to IO times alpha. This is true only if O is a fixed point. Otherwise, in general, it's not true, okay? I can say, or if O is the instant center of rotation, okay? But in general, the summation of moments about O is not equal to I0 times alpha, okay? One more subject, then I will stop. Inertia force. Inertia torque. Well, the Newton's law can be written as follows. Summation of forces minus the mass times the acceleration is 0. Okay. In which case, we can write Fi, well, not Fi, inertia force, to be minus MAG, okay, as you see. This is called the inertia force. So you can treat the MA force as if it's another force and treat your problem as a statics problem. And also you can say the moments about mass center minus the IG times alpha, right, is equal to 0. Okay. And the TI, therefore, TI is minus IG alpha is the inertia. So what you can do is use Fi and Ti, and solve a statics problem. Including inertia forces. Okay. So you can sum up the forces to 0, but you should be including the inertia force and the inertia torque in the problem. Okay, that's extremely important. Okay, that's all for today, if you don't have any questions. Anything you want to ask?
Hocam bir şey sorabilir miyim ben?
Evet, buyurun.
Derse geç katıldım da kaçırdım. Paper reviewing olacak mı acaba?
Ne? Anlamadım. Evet. Yani bu ya bu cuma ya önümüzdeki salı yapacağız onu. Ama hangi gün bilmiyorum. Yani
Tamamdır hocam.
duyuracağım size. Oldu mu?
Tamamdır. Teşekkür ederim.
Okay, thanks for listening then. I will stop sharing.
Have a nice day hocam. See you
And
later.
you too. Goodbye.
Have a nice day hocam.